Well, thanks for coming along to see what we're going to talk about. Thanks. I have to thank. Oh dear, why is that not on the screen? Bits. Okay, thank you very much. Thank you, Simajit, for the really exciting invitation to come here. Yeah, today, Simajit introduced me. So I'm a Nottingham Research Fellow. I'm an assistant professor at the University of Nottingham. Nottingham Research Fellow is it's a kind of scheme where they give people, it's kind of a career accelerator or something like that in the UK, where they try and minimise our teaching and maximise our research time. So it's a very nice place to work. My group is working on a range of different things. POMS are a part of it. I'm really a coordination chemist, working in a range of different systems for various catalytic functions. My background actually is in magnetism. A lot of the time when I was in Japan, where I was there for almost 7 years, was focused on molecular magnetism, spin crossover, electron transfer coupled spin transition, and so on. But towards the end of my time in Japan, I started looking at some things more around areas of molecular homogeneous catalysis, for example, water splitting, polyoxometalates, hybrid polyoxometalates, molecular photosynthesizers, and there's a whole range of different topics that we continue to look at in Nottingham. So I don't know how much people know about Nottingham. I realised I didn't even know that much about Calcutta, which seems embarrassing, but I learned some things on the drive here today. Nottingham is most famous for Robin Hood. I think that's probably true. I think there's a few question marks about Robin Hood, because I think probably firstly he didn't really exist, and then secondly he's actually from Sheffield, but Nottingham claims him, so we're fine. Nottingham is bang in the middle of England. I don't know if anyone can tell from my accent, but I'm from Scotland. I'm from Edinburgh up here, and I studied in Glasgow for a PhD before I went over to Japan. Nottingham's a really nice place to work. It's a beautiful campus. There's old bits, there's fancy bits where they put the people can study business and things. Then there's also this new carbon neutral lab, which is one of the supposed to be a sort of beacon for sustainable chemical research. And so Nottingham's making this huge investment, this huge drive at the moment towards green chemistry and so on. Just before I get started talking about where I fit into that kind of picture of green chemistry, I was saying to some of the guys earlier on, this is yesterday. I'm really confused with days. Sunday? No, Saturday actually. And I was in Scotland with some friends hiking, and it was beautiful, it was sunny the whole weekend, and everyone was saying, look, summer's here, it's boiling, it's so hot, and I landed here. I'm going to go relatively quickly through, and then we'll get on to more of the research end of it. I'm going to talk about a range of different things, and just starting off with the very, very basics of POMS, and then bring you up to what I'm doing, and where I see things going in the near future. So we start isopoly and heteropoly acids. This is generally the numbers of papers on POMS. This is from 2012, so it's not even, 2013, sorry, so it's not quite up to date. But it's clearly a rapidly expanding area, and of course, people like Professor Craig Hill are pioneers in this area. We're very lucky to have, and many of the other visitors as well. Polyoxometalates, for those who don't know, are typically constructed from these metals. They're molecular metal oxides, typically from these 5, but I'm going to talk mostly about tungsten. We've got 2 types of POMS. We've got POMS where we have just the metal and oxide, so just pure metal oxide molecules, like here, which we call isopolyanions or isopoms. And then we have heteropolyanions, heteropoms, where they have some templating group stuck in there. There's a massive family of POMS, which we won't go into too much detail, but the point is that there's a huge number of different shapes and sizes. They can be controlled in a lot of different ways. And the nicest thing really about POM research from the coordination chemist perspective is in some ways it almost seems like a blank page, you know. You can do so many things in the synthesis. You can control so much about it by relatively simple approaches. You know, a lot of it is one-pot chemistry, where we take a metal oxide salt. Typically, we add in acid, we mix it in water, and already we would have a polyoxometalate. You can control properties or topology, structure through changes in solvent, changing the cations, heteroatoms, of course, different types of templating reactions. And in some cases, also reducing templates as well. And the nice thing about the synthesis is that, broadly speaking, we're talking about pretty easy to do in terms of requirements, environmental requirements. So what happens in POM synthesis? You take your metal oxide salt, you add in your acid, you expand the shell, you get these octahedral building blocks. These octahedral building blocks stick together through condensation, reactions releasing water, and they're going to stick together in these different types of ways. Quite often when I talk at, even departmental things in the UK, there's a lot of people in the inorganic chemistry side of things don't necessarily always like the polyhedral representation of things, but I think in the case of polyoxometalates, it really does make sense because you can see that they just fit together into, shapes that you can relatively easily understand. Where the center of each of the polyhedra is one metal ion, and on the corners you've got your oxide ligands. So these are just some examples of the typical isopolyanions. We'll come back to mention them briefly a little bit later on. Where things start to get more, perhaps complicated or give you a lot more, controllability, I suppose, is where we start to include these template groups. In this situation, we would take our metal oxide building blocks, we'd add in acid, again, we form these octahedral building blocks, they stick together, and the final point is we have a template, and in this case that's a phosphate ion. The phosphate sits happily in the center with a kind of metal oxide shell around it to give us this polyoxometalate. Now, of the hetero-POMs, the heteropolyoxometalates, the typical structures that we look at, or the most common motifs, are this Anderson ion, Hagen, Wells-Dawsons. So we're going up from 6, for example, molybdenum, molybdate or tungstate, and then you can have a hetero metal in the center. In the Anderson, in the Hagen, you can have you have 12 tungsten or molybdenum, and so on, what's around your template. And the Dawson, you've got 18 of the metal oxide units. Okay, so we've zipped through very quickly the basics of the POMs. So if we have a look now at typical physical properties, I'll show you in a little bit how it is that I came to start working in POMs. But what I would say is that one of the key aspects that I find fascinating about them is the redox chemistry. The first thing I would say is, if you disregard these groups that are pinned on the top for the moment and just consider that this is a relatively normal cyclophotomegram for a Wells-Dawson, broadly speaking. What we have here is, as we scan in the negative direction, you've got multiple single electron reduction processes. And they're all pretty much reversible, quasi-reversible. So that's really nice because it means that with relatively little energy, relatively little work done, you can store multiple electrons per molecule. Reversibly, of course. Now, where I think it gets really interesting as well is just how much conditions play a role in this. Because if you change the cation, you change the solvent, okay, you can have a huge influence on the redox potentials. So you can think about this as changing the energy levels at which electrons are added. So we shift in water compared to DMF, we're far more positive LUMO energy, lower energy LUMO, and you can see that generally the properties are maintained. So we've seen a shift. But you might notice that there's something else in here as well. We seem to have grown an extra peak. And what that is, if we typically count this as 1, 2, 3, and 4, shifted from those 4 there, we have these extra little ones in here. What you can see is over here, you've got an additional effect that we didn't account for before, which is if we have, based on the pH of the system, we can have this protonation effect. So what it means is that from one relatively simple molecule, you've got a huge number of potential redox states you can access, and you can tune that specific electrochemistry. The other thing that comes with POM electrochemistry is some spectroscopy, or in kind of more simple terms, color changes. So what we have, if we just take, for example, Wells-Dawson, and in a typical situation, if you have just a fully oxidized Wells-Dawson, where all of these tungstens are in a 6+ oxidation state, we've got a totally, well, a colorless powder or solution. If we add an electron, and that can be done, we can photo-reduce it, or electro-reduce it, or so on, chemically reduce it, we change from colorless to dark blue. And that's because we introduce these electrons, they're delocalized, we have these intervalence charge transfer transitions, and we can essentially see that you've got a completely different thing before and after. Now, if we look at the absorption spectra of a typical POM, and this is going back to the one that we just looked at, the electrochemistry form, you can see that there's almost no absorption really in the visible range. We're talking, you've got this ligand to metal charge transfer around here, but there's not much happening up here. But as we start to put electrons onto it, that changes. If we go to the first reduction process here, we have a peak growing around about 800 nanometers and a peak around about 1500 or so. As we add a second electron, those peaks change. And we now have a peak around about 650 and one around about 14 or 1450 or something. So what you can see is that the reduced state, the number of electrons on the POM, essentially has a spectroscopic fingerprint that you can understand precisely how many electrons are on that molecule at any one time. It's very useful when we're going to look at the applications. We continue. The third process, we see further shifts, and the fourth reduction, some more shifts as well. So when we go back to the initial absorption spectrum flow, you can see that what we do have in that initial case is this ligand to metal charge transfer. If we were to irradiate that, what would happen? This takes us on to the kind of the area of general polyoxometalate photochemistry, photocatalysis. If we irradiate the ligand to metal charge transfer band, the tungsten oxide motif here, we irradiate it, we essentially put one electron onto the tungsten, reducing the tungsten, and we leave one radical on the oxyl group, which is clearly highly active and can do work for us. So we irradiate this, obviously we're irradiating with UV light. We irradiate in the presence of different solvents, or in different cases different substrates, we can do different chemistries. We take our which is just a representation of the polyoxometalate. We irradiate the MO. We have we form a radical in the oxygen. In the presence of water, we abstract a hydrogen. We form these reactive hydroxyl species, which will be involved in follow-up reactions. They can directly oxidize different organic groups. Likewise, in the presence of alcohol, we can irradiate the polyoxometalate, we form the radical excited state, we abstract the hydrogen again, and in this case here, the alcohol can then be subsequently oxidized onwards. So the conditions play a big role in the kind of catalysis, the kind of chemistry we can do with the POMs. We know that we have this strong absorption in the UV region. If we do the excitation, we excite from the ground state to the photoexcited state. From there, the catalytic cycle typically goes excitation of the POM, something to reduce the POM, something to donate an electron, and typically a proton. We have our stable, relatively stable, reduced polyoxometalate, which can then be reoxidized, for example, by air, to cycle. So this is a really, really neat process. It's very high energy. We can do a lot of different organic chemistries using these polyoxometalates. This paper here in Chems.Rev is a really nice summary of it, and there's a few people who've done some excellent work on this process. We can do all sorts of different oxidation reactions. We can do aliphatic, alkanes, alcohols. We can do aromatics, oxidase N. We can do all sorts of different oxidation catalysis. So, as I said, we won't go too much into detail. I'll come back. I just have to touch on that for now. Now, one of the areas of polyoxometalates that has yielded the most exciting results over time, and this is in particular Professor Hill has done incredible work in, is what we call Lacunary polyoxometalate. In this case here, we take a tungsten oxide cluster. We can vary the pH, which allows us to remove 1, 2, or 3 metal centers from the polyoxometalate. So we've essentially kept our relatively stable shell, which has so many nice properties that we've already discussed, but we've now made all these gaps that we can exploit to do any chemistry that we like. For example, just looking at the most simple kind of examples of the 1, 2, and 3, well, almost more simple. You can see that we can just stick in different transition metals that will allow us to do all sorts of different catalysis with it. CO2 activation, alkane oxidation, water oxidation, and there's far more examples from those as well. Now, the really nice thing about this is that when you remove these metal centers from the polyoxometalate, you leave yourself binding sites. And you can leave yourself different numbers of binding sites, different shapes of binding sites, and so on. But from my perspective, the most exciting, in my research, what we're really focusing on is derivatizing these in a different way. And that is looking at these organic-inorganic hybrid polyoxometalates. There's a few groups looking at these in the world, and there's a few different types of hybrids. And so we can talk about class 1 and class 2, where broadly speaking, class 1 is through weak interactions. The polyoxometalate is an anion, a polyanion. And so clearly we can have electrostatic interactions with cations. There can be, there's good opportunities for hydrogen bonding interactions between POMS and hydrogen bond donors. Of course, that involves interactions. But what my group look at in particular with polyoxometalates is this class 2, which is where we covalently hybridize through coordination of bonds. Now, of these class 2 covalent hybrid polyoxometalates, there's a few different classes, and we're going to look at some different ones to try to understand what's going to work best for us. Perhaps the most reported, most studied, is this alkoxide, so tris alkoxide linkers. And here you can, for example, take your alkoxide group connected directly onto Anderson clusters, which is this 7-metal disk, basically, or to Dawson clusters like that. And there's some excellent work that's been done on these. I'm missing the reference, but it's from a good place. Where we've looked at it, this is a while ago, I think when I was doing my PhD, I thought Pradeep might have been here, so I also like to show Pradeep's paper on this. But what you can do is, for example, you can take a vanadium-3, that's 3 vanadiums up there, this is tungsten-15, and then you add in your tris alkoxide. You cook it in acetonitrile, and then you've got your group stuff on the top. And the really nice thing that you can do with this is you can control, for example, the interactions in crystal lattice or so on. You can have pretty amazing supramolecular chemistry of enormous clusters. And we can follow that formation as well by mass spectrometry. I was really interested, when I started in this kind of work with polyoxometalates, I was really interested on the magnetic side. And one of the things I thought about was connecting these kind of DPP dipyracylpyridine ligands via this tris alkoxide linker onto the polyoxometalate, connecting an iron and looking for spin crossover. And to be honest, it didn't work that well. But what I found that was quite useful from my perspective as well was that the electrochemistry is also a little bit limited. when you go for these different types of linkers. So, based on that, and based on electrochemistry being one of the fundamental things that we needed to exploit in our systems, we changed our plans. And we had a look at the organotin, the organophosphonate, or organosiloxane groups. How these ones work? We knock out one metal center, so that's we essentially add a little bit of sodium hydrogen carbonate. We remove the tungsten oxide. We leave ourselves one vacancy on the polyoxometalate core. And then into that vacancy, we can stick, for example, that can be a tin, so it's a heteroatom. And that can have an R group of almost any kind. So of those three, which I kind of grouped together for simplicity, the nice thing is that we've got the tin, the siloxane, the phosphonate linkers. All of them have, well, broadly similar structures in that we have our heteroatoms connected into that vacancy, although the tin is just a single tin.